Welcome dear learners. Welcome to the course Quantum Chemistry. In this module, we are discussing photoelectric effect and Compton effect. These are two important phenomena that cannot be explained on the basis of classical mechanics. First of all, the major contents of this module. Photoelectric effect, it's a definition. The photoelectric effect, it's a characteristic features. Einstein's photoelectric equation, Compton effect and a description on the Compton effect, equations for Compton effect, the Compton wavelength and numerical problems. First of all, photoelectric effect. The photoelectric effect was first documented in 1887 by German physicist Heinrich Hertz. This effect is further characterized by Philip Lenard in 1902. The definition of photoelectric effect. The ejection of electrons from surface of a metal when light of suitable frequency strikes on it is called the photoelectric effect. Electrons emitted in this manner are called the photoelectrons. These are incident light photons which strikes on a metal surface, and a consequence of that, electrons are emitted from the surface of the metal. The emitted electrons are the photoelectrons that can be amplified and converted into a current. That current is called the photoelectric current. Now, important characteristics of photoelectric effect. For each metal, a certain minimum frequency of incident light is needed to eject the electrons. This minimum frequency is termed as the threshold frequency, denoted as nu zero. A light of smaller frequency than nu zero cannot eject the electrons. That is, photoelectric effect is not possible if you are using a frequency lower than that of the threshold frequency nu zero. The threshold frequency is different for different type of metals. That is, threshold frequency vary from metal to metal. The kinetic energy of ejected electrons, that is, the photoelectric effect create electrons, and the kinetic energy of the ejected electrons is independent on intensity of the incident light. But the kinetic energy has a linear relationship with frequency. This means the kinetic energy of the photoelectrons directly proportional to the incident frequency. That is, with increase in frequency, there is an increased kinetic energy is observed. The number of ejected electrons from the metal surface depends upon the intensity of the incident radiation. That is, if there is an increase in the intensity, the number of ejected electrons will also increase. The greater the intensity, the larger is the number of ejected electrons. Now, explanation of photoelectric effect. The photoelectric effect cannot be explained on the basis of classical wave theory of light. That is, failure to give suitable explanation to photoelectric effect is one of the notable drawbacks of classical mechanics. The quantum theory of radiation affords an easy explanation for the photoelectric effect. Albert Einstein explained the phenomenon of photoelectric effect based on Max Planck's quantum theory. Max Planck, in his quantum theory, provided an idea of quantization of energy. that we already discussed in the first section, that the Max Planck's quantum theory is an implication of an important phenomena, that is nothing but quantization of energy. We know the postulates like E is equal to h nu, E is equal to nh nu, etc. Now, the explanation of photoelectric effect was performed by Albert Einstein based on the same quantum theory proposed by Max Planck. Now, we can move on to the explanation by Albert Einstein. Here, Einstein derived one important equation called Einstein's photoelectric equation. We are moving to Einstein's photoelectric equation. Let a photon of frequency nu is falling on a metal surface. Then, according to Max Planck's quantum theory, the energy associated with a radiation of frequency nu is equal to h nu. That is, you are providing h nu energy to a metal surface. This energy is utilized for two purposes. One portion of this energy is used to remove electrons from the metal surface, and the remaining energy is to provide kinetic energy. Thus, h nu is equal to h nu 0 plus kinetic energy. Here, h nu 0 is the energy required to remove electrons from the metal surface. This term h nu 0 is otherwise known as work function, and work function can be marked as phi. That is, work function is the amount of energy required to remove electrons from the metal surface. So, total energy h nu is equal to phi plus kinetic energy. That is, h nu 0 plus half mv square, where v is the velocity, half mv square represents the kinetic energy. On rearranging, h nu is equal to h nu 0 plus half mv square. On simple rearrangement, h nu minus h nu 0 is equal to half mv square. 2 into h nu minus h nu 0 is equal to mv square, or 2h into nu minus nu 0 divided by m is equal to v square, or simply v is equal to under root 2h into nu minus nu 0 divided by m. These relations, number 1, number 2 or number 3 are different forms of Einstein's photoelectric equation. Now, in a simple way, we can also interpret this equation in another form. That is, h nu is equal to phi plus stopping potential. Stopping potential. Stopping potential. What is meant by the term stopping potential? By comparing these two equations, it is clear that kinetic energy is replaced by the term stopping potential. Suppose we are providing an energy equal to kinetic energy to the ejected electrons in an opposite direction. We can stop that photoelectron. So, energy required to stop the photoelectron is termed as the stopping potential and is expressed in electron volt. Thus, we can also get an equation h nu is equal to work function plus stopping potential. This is another form of Einstein's photoelectric equation. Thus, two important parameters are phi is equal to h nu 0 and stopping potential is the kinetic energy in electron volt. And it should be noted that nu 0 shown in all these equations represents the minimum energy required to just start the photoelectric effect, that is simply the threshold frequency. Thus, we can use these equations as per our convenience for solving different numerical problems. Now, some numerical problems based on photoelectric effect. The first problem, the work function of sodium metal is 2.92 into 10 raised to minus 19 joule. Calculate the threshold frequency of sodium metal. This is a direct problem where the value of work function is given. It is clear that work function is related to threshold frequency by the relation work function phi is equal to h nu 0, where nu 0 is the threshold frequency. This is the relation between work function and the threshold frequency. We have to find out the value of threshold frequency. So, threshold frequency nu 0 equal to work function divided by Planck's constant. We can substitute the data to get the final value of the threshold frequency. That is, phi is given as 2.92 into 10 raised to minus 19 joules. And we know about Planck's constant h, its value is 6.626 into 10 raised to minus 34 joule second. Unit joule cancels and we will get the final numerical value of threshold frequency nu 0 as 4.40 into 10 raised to 14. This second goes to the denominator and the unit is second inverse. This is simply represented as hertz. Thus, the threshold frequency of sodium metal is equal to nu 0 is equal to 4.40 into 10 raised to 14 second inverse or hertz. This is the final answer to the problem. Now, another problem based on the photoelectric effect. Here, a photon of wavelength 4000 angstrom strikes a metal surface with the work function 2.13 electron volt. We have to calculate two things: the energy of the photon, energy of the incident photon in electron volt, and the kinetic energy of the emitted photoelectron. It should be noted that the work function is given in electron volt. Therefore, we have to first find out the energy of the incident photon of wavelength 4000 angstrom in electron volt. That is, we have to find out the energy of the photon of wavelength 4000 angstrom in unit of electron volt. After that, we can calculate the kinetic energy. First of all, the incident wavelength lambda is 4000 angstrom, that is 4 into 10 raised to 7 meter, 10 raised to minus 7 meter, and lambda is 4 into 10 raised to minus 7 meter. On suitable substitution, lambda can be converted to energy. The relation is E is equal to h nu h c by lambda, that is equal to 6.626 into 10 raised to minus 34 joule second into 3 into 10 raised to 8 meter per second divided by wavelength, that is 4 into 10 raised to minus 7 meter. It should be noted that on solving this, we will get the energy in joules. And we have to convert the obtained energy in joules to the unit of electron volt by using the conversion factor. 1 electron volt is equal to 1.602 into 10 raised to minus 19 joules. So we have to divide this quantity by 1.602 into 10 raised to minus 19 to get the final energy in electron volt. That is, I am dividing this quantity with 1.602 into 10 raised to minus 19. The final value will be 3.10 electron volt. 3.10 electron volt. That means the 4000 angstrom wavelength corresponds to an energy of 3.10 electron volt. That is, in this problem, you are providing a photon of energy 3.10 electron volt. The first part of the problem is over, and we can move on to the second part, that is, find out the kinetic energy of the emitted photoelectron. For this purpose, we have to use Einstein's photoelectric equation. The equation is total energy provided h nu is equal to work function phi plus kinetic energy, and kinetic energy equal to total energy provided minus work function. And we already calculated that the total energy provided is 3.10 electron volt, and the work function is 2.13 electron volt. Thus, the kinetic energy of the ejected photoelectron is equal to 3.10 electron volt minus 2.13 electron volt. Thus, we will get the kinetic energy value as 0.97 electron volt. This about the second part of the problem. Thus, the Einstein's photoelectric equation is very important. H nu equal to phi plus kinetic energy, that is work function plus kinetic energy. Now, the conclusions based on photoelectric effect. The photoelectric effect provides evidence for the particle nature of light. The photoelectric effect also provides evidence for quantization. If light shines on surface of a metal, there is a point at which electrons are ejected from the metal. Now, we can move on to second part of the present module, that is Compton effect. Arthur Compton, that is shown in the picture. Arthur Compton found that if monochromatic X-rays, that is X-rays of same wavelength, are allowed to fall on carbon or some other light element, the scattered X-rays have wavelength larger than the incident X-rays. This effect, This phenomena is known as Compton effect. That is, scattered X-rays have a higher wavelength than the incident X-ray. There is a wavelength shift is noted. That wavelength shift between scattered X-ray and incident X-ray is known as Compton shift. We can move on to the details of the Compton effect. This is the pictorial representation. Here the X-rays are using these X-rays struck on light element surface. Light element like a carbon surface. In the surface of such elements, there are electrons. And the X-rays of fixed wavelength is scattered by the electrons present on the non-metal surface. This implies that electrons are ultimate scatterer, and the scattered electrons have scattered through certain angle that is marked as phi in this pictorial representation. At the same time, the photons are, the X-rays are also scattered. The scattered X-rays are through certain angle, and that angle is marked as the scattering angle theta. The scattering angle theta is an important parameter as far as the wavelength shift is concerned. Let lambda is the incident wavelength of the X-ray photons, and lambda dash is the X-ray wavelength during scatter, and the scattering angle is theta. Scattering angle of X-ray is theta. The wavelength shift between scattered X-rays and incident X-ray, that is lambda dash minus lambda. This difference is termed as delta lambda. This delta lambda is known as the Compton shift, and this Compton shift is having important connection with the scattering angle theta, that is the angle through which X-rays are scattered. We will move on to the details later. Now we can derive some important equations associated with the Compton effect. As I already mentioned, the incident wavelength is always lower than the scattered wavelength. Let the incident wavelength of the X-ray is lambda. The scattered wavelength is lambda dash. Then Compton observed that lambda dash greater than lambda. So lambda dash minus lambda will be a positive quantity, and this quantity is marked as delta lambda. This term I already mentioned, known as Compton shift. It should be noted that the Compton shift is related to scattering angle theta of the scattered X-rays. Arthur Compton used two important relations that are used to find out the Compton shift from scattering angle theta. The two relations are delta lambda or Compton shift or wavelength shift is 2h by mc into sin square theta by 2. I mark it as equation number 1. This equation uses sin theta or sin function, where theta is the scattering angle. We can also change equation 1 to a cosine function. That is, by using trigonometrical relations, this can be transformed to a cosine function. The new relation is h by mc into 1 minus cos theta. I mark it as equation number 2. That is, wavelength shift is related to scattering angle theta in equation 2 as well as in equation 1. Equation 2 is more conveniently used for the calculation of wavelength shift or Compton shift. Now, we can do some numerical problems based on the Compton effect. And the problems are to find out the Compton shift delta lambda. In this problem, we are going to calculate the Compton shift delta lambda when the scattering angle theta is equal to 0 degree. Scattering angle theta is equal to 0 means the scattered radiation is parallel to the incident radiation. The scattered radiation and the incident radiation are parallel to each other. We are going to find out the wavelength shift in that circumstance. We can use the relation delta lambda equal to h by mc into 1 minus cos theta to find out the wavelength shift. And theta is equal to 0 degree. This situation is that scattered radiation is parallel to the incident radiation. And it should be noted that cos 0 is equal to 1. On substituting this, we will get delta lambda equal to h by mc into 1 minus 1. That is 0. This implies that when the scattered radiation is parallel to the incident radiation, that is, if the scattering angle is 0 degree, the wavelength shift is also 0. That is, no Compton effect is observed. This implies that incident wavelength is the same as scattered wavelength. If theta is equal to 0, there is no Compton shift. This is an important information as far as Compton effect is concerned. We have to keep some important values of sin theta and cos theta for the sake of doing the problems. And I will show you a chart simply depicting common angles, their sine values and cosine values. And this is the chart. Angle theta, it may be 0 degree, 30 degree, 45 degree, 60 degree and 90 degree. First of all, sin theta 0, 1 by 2, 1 by root 2, root 3 by 2, 1. And cosine function, cos theta, just opposite to that of sine function. That is 1 root 3 by 2, 1 by root 2, 1 by 2 and 0. From this chart it is clear that cos 90 is equal to 0. This is a useful chart as far as some numericals about Compton effect is concerned. Now, another problem, that is, calculate the Compton shift delta lambda when the scattering angle theta is equal to 90 degree. What is this situation? Here, incident X-ray and scattered X-ray are mutually perpendicular to each other. Hence the scattering angle theta is equal to 90 degree. Thus, we can use the relation delta lambda equal to h by mc into 1 minus cos theta, again for finding out the Compton shift. And on substituting various values, h by mc into, first of all, cos 90. Cos 90 is equal to, cos 90 is equal to 0, that is 1 minus 0, that is delta lambda is equal to h by mc. We can also put the numerical values of Planck's constant h, mass of electron m, and velocity of light c. On substituting, we will get delta lambda equal to 6.626 into 10 raised to minus 34 joule second divided by mass of electron, that is 9.1 into 10 raised to minus 31 kilogram, into velocity of light, that is 3 into 10 raised to 8 meter per second. On suitable simplification, we will get delta lambda equal to 2.42 into 10 raised to minus 12 meter. That is, the wavelength shift is 2.42 picometer. This is another important observation. Thus, we will get the final value of delta lambda or Compton shift as 2.42 picometer. This implies that when scattered X-rays are perpendicular to incident X-ray, that is at a scattering angle theta is equal to 90 degree, the wavelength shift is 2.42 picometer. This value 2.42 picometer is known as Compton wavelength. That is, Compton wavelength is the wavelength shift or Compton shift at a scattering angle 90 degree. That is, the Compton wavelength is a constant value that is equal to 2.42 picometer. We can move on to one more problem based on the Compton effect. Here, we are going to calculate the Compton shift delta lambda when the scattering angle theta is 190 degree. We can also use the same equation to get the result or to get the value of delta lambda. The relation is delta lambda is equal to h by mc into 1 minus cos theta. It should be noted that cos n pi, where pi is 190 degree, cos n pi equal to minus 1 raised to n. Here cos 190, cos 190, cos 190 degree, that means cos pi, cos 1 pi, that is minus 1 raised to 1, that is equal to minus 1. Substituting the value of cos theta here, we will get delta lambda equal to h by mc into 1 minus minus 1. The result is 2h by mc, 2h by mc. On substituting, 2 into 6.626 into 10 raised to minus 34 joule second divided by mass of electron 9.1 into 10 raised to minus 31 kilogram into velocity of light, that is 3 into 10 raised to 8 meter per second. We will get the final value 4.824 picometer. 4.84 picometer. Moreover, you can also make a simplification here. We already learned the fact that H by mc is equal to 2.42 picometer, which is known as the Compton wavelength. Therefore, here in this problem, delta lambda is 2h by mc. This h by mc value is 2.42. So, final result is 2 into 2.42. 2 into 2.42. That is also equal to 4.84 picometer. Thus, in this module, we have discussed about two important phenomena. The photoelectric effect, different equations and problems based on that, and the second effect, the Compton effect, different relations and problems connecting the Compton effect. That all about the present module. Wish you a warm learning experience. Thank you all.